In the previous videos, we have discussed about the steps of designing pre-stressing members. We usually start with determining the stress acting within the beam and checking it against the limits. In these videos, we're going to discuss how do we determine the stress acting in a pre-stressing members. This is provided that the section has been proposed and we know the geometrical properties of the sections. This slide demonstrates the principles of pre-stressing. You know that pre-stressing is basically inducing stress onto the member so that it generates resistance to counteract the external load. The stress that develops in the beam can be due to the axial compressions, bending, and eccentricity. And the principles of prestressing is on basis of the principle of superpositions. Assuming that the concrete is elastic, the total stress in the members will be the summations of the effects of the axial compression, bending, and also eccentricity. First, let us look into the reinforced concrete structure. Assuming this is a simply supported reinforced concrete beam, the UDL will be the external load. The simply supported beam is supported at both ends. Based on the principle of static equilibrium, you are able to determine its shear force diagram and bending moment diagram. Now we will need to determine the stress in the member. There will be two critical parts of the simply supported beam, which is the section AA at the midspan and section BB at the support. The diagram here shows the stress in the beam at the midspan, and the diagram here shows the stress at the support. For a typical reinforced concrete beam, no prestressing load is applied onto the member. The member is purely subjected to an UDL, which will lead to bending moment acting on the member. Based on the bending moment diagram, we know that the moment at the support will be equals to 0, while the moment at the midspan will be the largest. This is the reason that we look into two critical points of the member. Now we look at the stress at the midspan. The UDL will cause bending to the beam. This bending response will cause tensile stress at the bottom of the beam and compression stress on top of the beam. In terms of the stress, we will take negative to represent tensile and positive to represent compressions. If you cut the sections of the beam here, the internal stress will become external stress. It should theoretically look something like this, where there is a neutral axis. At the bottom part of the beam there will be tensile stress, and at the top part of the beam there will be compressive stress. Assuming that the stress is linearly distributed throughout the cross sections, that will give a straight line for this stress diagram. Therefore, the stress at section AA due to bending will look something like this. As there are no other external load, the stress within the beam member for the reinforced concrete, it will be purely due to bending. Therefore, the final stress within the sections will be the same as the bending. As for the support, there is no bending moment. With that, the beam is assumed with 0 bending stress and there is no external load. the total stress will be zero bending as well. Now we look into the effect of the axial compression. For the pre-stressed concrete member, a compressive force is applied along the neutral axis of the beam. On top of that, there are UDL acting on the beam as the external load. The compressive pre-stressing force generates an axial stress acting along the cross-sections of the beam. This compressive force will cause the entire section here to be in compression. Assuming that the compressive stress is equally distributed throughout the cross-sections of the beam section, the axial stress will look something like this. Then there will be bending caused by the UDL, which will give you tensions at the beam soffit and compressions on top of the beam. That give you a bending stress, something like this. Based on the principle of superpositions, these two stress can be added up together to become a total stress acting on the member. The total stress on top of the beam will be the summations of these two compressive stress. And the total stress at the soffit of the beam, it will be this minus this. The compressive stress and the tensile stress, they can cancel out each other, and what is left over, it will be the total stress acting on the soffit of the beam. Next, we look at the support of the pre-stressed concrete. The pre-stressing compression force will cause axial compressions onto the beam element. However, as the section here is at the support, there is no moment generated by the external UDL load. Therefore, the total stress acting at the support here, it will be same as the axial force acting on it. Now let us look into the third case of the pre-stressing principles. There are pre-stressing force acting on the beam, and the force is acting at an eccentricity distance from its neutral axis. Also, there will be UDL acting as the external load onto the beam. Due to the compressive force caused by the pre-stressing load, there will be axial force acting on the member. Due to the external load acting on the beam, there will be bending moment stress acting on the member, tension at the bottom of the beam, and compressions on top of the beam. There is one more consideration here, is due to the effect of the eccentricity. When the compressive force is applied at the eccentricity lower than the neutral axis, it will generate high compressive stress at the bottom of the beam, which subsequently shorten the bottom part of the beam and leads to the tensions at the top of the beam. This gives a compressive stress at the bottom of the beam and tensile stress on top of the beam. Based on the principle of superpositions, the total stress acting on the members will be the summations of the three effects. The stress on the top of the beam will be axial compression plus the bending minus the eccentricity. As for the total stress at the bottom of the beam, it will be the axial compressions minus the bending plus the eccentricity. Next, we look at the support regions of the pre-stressed member. There is a compressive force acting on the beam. This will give you the axial stress. the UDL do not cause any bending moment acting at the support. For that, there is no bending moment. And what you see at the support here, there is an eccentricity. Therefore, the effects of the eccentricity needs to be considered. Based on the principle of superpositions, the total stress on top of the beam will be the axial stress minus the stress due to the eccentricity. As for the stress at the bottom of the beam, it will be the axial compressive stress plus the stress caused by the eccentricity. What you see here is the stress in the prestressing members can be caused due to the three main components, which are the axial, bending, and eccentricity. In fact, these principles can be applied for various cases of the prestressing conditions. For example, for the external load other than UDL, such as point load, you will need to first determine the bending moment diagram and find the locations with the maximum and minimum bending moment diagram. Those are the likely regions of the critical conditions. So when there is a bending moment, the effects of the bending as a result of the bending moment need to be considered. For the regions without bending moment, the effect of the bending moments needs to be omitted. Also, you will need to observe if there are eccentricity. In some conditions, there may be eccentricity at the midspan but no eccentricity at the support. In that case, for the midspan, you will have to consider the effect of eccentricity. Then, for the support without eccentricity, the effects of the eccentricity cannot be considered. It is also noted that the positions of the compressive load is also important. If the compressive load is applied on top of the neutral axis, that will give a totally different response in terms of the effect of the eccentricity. Under such circumstances, the diagram of the eccentricity will have to be flipped left and right because the compressive force is above the neutral axis. In short, for you to analyze the stress within a prestressing members, you need to consider all the effects of the external load acting on the member. After you have established all the stress diagram, then apply the principle of superpositions. The summations of all the stresses will be equals to the final stress acting on the member. Normally, you will need to check for the top of the beam and bottom of the beam, as these two normally represent the most critical situations in the beam section.